Hi, welcome to How the Measured Lifetime of the Tau Lepton Changed over 30 years. So this video is the second part in a two-part series on the measurement of the lifetime of the Tau Lepton. The first video in this series was called The Lifetime of the Tau Lepton. There we looked at the motivation and the basic experimental methods used in measuring the Tau lifetime. Now, that video is not strictly needed in order to understand what's going on here, but we would recommend that you watch it in order to get a more complete picture. Here, we're going to look at the experimental results and how they changed over time. So we'll see how the measured value of the lifetime of the Tau Lepton has changed since the early 1980s. Now, an important point is that we are not saying that the lifetime of the Tau Lepton changed over those 30 years. But experiments improve, and that means that the measured value can change over time. And this is an example of how scientific understanding evolves with time. Also, we hope that this video will be a good demonstration of what Gaussian error bars are. So, for example, if one experiment measures the Tau lifetime to be 290 plus or minus 10 femtoseconds, does that mean that the true value of the Tau lifetime is between 280 and 300 femtoseconds? No, it doesn't. In fact, it doesn't even tell you the probability that the true value of the Tau lifetime is between 280 and 300 femtoseconds. But we will see what it does mean. Okay, so with that, let's look at the experimental results. Now, before we look at the experimental results, I should mention one caveat. This is not an exhaustive list of all Tau lifetime measurements. What I did is I took the experiments listed in the Tau lifetime section of the particle data group listings from 2020. Now, one thing that's important to know is that the PDG may have applied some selection criteria to choose what results they listed. For example, if an experiment was later found to have some problem, the PDG may not have included it in their listings. And also there may be other criteria that I don't know about. However, the references to the experiments can be found in the PDG document, and I've given a link to that document in the description below. Okay, so here are those results, starting with the 1982 result from the Mark II experiment and going up to the result from the Belle experiment in 2014. Now, the error bar on that original Mark II result from 1982 is quite large, and it makes it a little bit hard to see the details in the rest of the plot. So I'm going to redraw this plot with the Mark II result off the top of the page. Okay, so now we can see the results a little bit better. And we can see that the error bars shrank as a function of time. In fact, let's look at that in detail. How did the experimental uncertainty change with time? Okay, so first we have that Mark II result from 1982. The experimental error bar on that result was 190 femtoseconds. Then we had a cluster of results from 1987 to 1995. These results had error bars that were about an order of magnitude smaller, so they ranged from 10 to 29 femtoseconds. Next, we have a group of results from 1996 to 2004. These had error bars that ranged between 1.7 and 4.9 femtoseconds. And finally, in 2014, we have the Belle result that had an error bar of only 0.62 femtoseconds. Okay, so let's see if these historical results form a coherent picture given what we know now. So the Belle 2014 result, which was 290.17 plus or minus 0.62 femtoseconds, has an error bar that is much smaller than that of the other results. The next best result was from Delphi in 2004, and it measured the tau lifetime at 290.9 plus or minus 1.7 femtoseconds. So it had an error bar that was almost 3 times as large. So let's imagine that the true value of the tau lifetime is the central value of the Belle result, so that the true value of the tau lifetime is 290.17 femtoseconds. And then let's ask the question, does the scatter of the other results make sense? Now, we should note that this is a bit of a cheat. We don't know the true value of the tau lifetime, and we don't even know that it's within the Belle error bar. But we want to do something that's simple here. So what we're going to do is the following. We're going to take Belle's tiny error bar as an indication that the true value of the tau lifetime is very close to 290.17 femtoseconds. And we're going to ask if the other results are reasonable under that hypothesis. We will, however, mention the relevance of Belle's error bar in these comparisons as we go along. Now, we should mention a couple of assumptions that we're going to make. We're going to assume that the errors on the results of the different experiments are uncorrelated. And we're going to assume that the errors on the experimental results are Gaussian distributed. Now, this is not necessarily true, but it is often a very reasonable assumption. But let's quickly remind ourselves what it means for experimental errors to be Gaussian distributed. Okay, so let's say we're measuring some observable, Q. In our case, Q would be the lifetime of the Tau lepton. Q true is the true value of Q. Q measured is the measured value of Q. And because there is measurement error, Q measured will not equal Q true. So we're taking the measurement errors to be Gaussian distributed with an uncertainty that we're going to call sigma Q. And so now let's see what that means. If we did the experiment many times, the measured values Q measured would be Gaussian distributed around Q true. And that Gaussian would have a standard deviation of sigma Q. So here we've plotted the probability density for Q measured. Most experiments would give results near Q true, but a few would be far away. In particular, Q measured would fall within the range from Q true minus sigma Q to Q true plus sigma Q in about 68% of the times we conduct the experiment. Q measured will fall within the range from Q true minus 2 sigma Q to Q true plus 2 sigma Q in about 95% of the times that we conduct the experiment. If you'd like some more information, there are a few videos on this channel that you can check out. So for more details on the Gaussian distribution, you might want to look at Features of the Gaussian or Normal Distribution, Part 2, Probability Bands and the 68, 95, 99.7 rule. And if you'd like to know why assuming Gaussian distributed errors is often reasonable, you can check out the playlist Mini Course on Error Bars, Measurements, and Decision Analysis. Okay, so with that, let's take a look at that first result from Mark II from 1982. So the Mark II result was that the tau lifetime was measured to be 460 plus or minus 190 femtoseconds. Now, as we said, we're assuming Gaussian errors. So if the experiment were repeated many times, we would expect the measured values would be Gaussian distributed around the true value. And because the measurement uncertainty is 190 femtoseconds, we would expect the standard deviation of that Gaussian to be 190 femtoseconds. So here we've drawn a Gaussian with a standard deviation of 190 femtoseconds, and we would like that to be centered at the true value of the tau lifetime. Now, of course, there's the problem that we don't know the true value of the tau lifetime. So instead, we take the central value of the Belle 2014 result. So that result was 290.17 plus or minus 0.62 femtoseconds. And we're going to take that as a good approximation of the true value of the tau lifetime. And I'd like to note that the width of the blue line in this plot is the Belle error bar. And I don't mean the width of the blue arrow, I mean the width of the very, very thin blue line. Okay, so as we said, the Mark II result from 1982 was 460 plus or minus 190 femtoseconds. So the 190 femtoseconds defined the width of this Gaussian that we've drawn, but 460 femtoseconds was their actual measured result for the tau lifetime. Now we can see that their measured result is less than 1 sigma, so less than 190 femtoseconds, away from the central value, which we've defined to be the Belle result of 290.17 femtoseconds. We can see from this plot that the result from 1982 looks very, very reasonable in hindsight, knowing what we know now. And I want to emphasize that this plot could not have been drawn in 1982. The experimenters on the Mark II result knew of their measured value of 460 femtoseconds, and they knew what their error bar was of 190 femtoseconds, but they had no idea what the later, more precise Belle result would be, so they could not have drawn this plot. So I just want to point out that this plot is really a testament to how well the Mark II experimenters estimated their experimental uncertainty. Now, as we said, we would like to have drawn this Gaussian centered at the true value of the tau lifetime. And the Belle 2014 result is not the true value of the tau lifetime. However, even if the true value differs from the Belle result by a few times the Belle error bar, our conclusions won't change. Okay, so now let's compare that Mark II result with the next result in our plot. So the next result is from the Mack experiment, and they measured the tau lifetime to be 309 plus or minus 19 femtoseconds. Okay, so as we just said, the Mack result was 309 plus or minus 19 femtoseconds. Again, we expect the measured result to be Gaussian distributed around the true value of the tau lifetime. Here, because their experimental uncertainty is 19 femtoseconds, we expect that Gaussian to have a standard deviation of 19 femtoseconds. And we can see that the Mack Gaussian is much narrower than that of Mark II, which had a standard deviation of 190 femtoseconds. So Mack's measured result for the tau lifetime was 309 femtoseconds, and their estimated measurement uncertainty was 19 femtoseconds. We've marked that value of 309 femtoseconds with a tiny star in the top plot. So this means that their measured result was just about 1 sigma, so 19 femtoseconds, above the Belle 2014 value of 290.17 femtoseconds. So again, just like the Mark II result, the Mack result was very reasonable given their experimental uncertainty. And again, our conclusions would not change even if the true value of the tau lifetime differs from the Belle result by a few times the Belle error bar. Okay, so now let's compare that Mack result to the rest of the experimental results that occurred in this cluster between 1987 and 1995. In these experiments, the experimental precision varied between about 10 and about 29 femtoseconds. Okay, so here we have a plot. Here the bottom plot is the previous Mack result that we just saw. I should note that we've changed the scale. So now the blue line is still the width of the Belle error bar, but you should note that now it's a bit wider because we've zoomed in on these results. Again, the error bar on each experimental result defines the width of the Gaussian, and the central value of each experimental result is marked with a tiny star. So comparing these results, we can say that in hindsight, these results are in reasonable agreement with the Belle 2014 result. The largest deviation comes from Clio from 1987, and that deviation is about 1.5 sigma. It is a little bit unusual that 8 of these results fell above the Belle result and only 1 fell below, but it's not that unusual. Now, out of the results from this cluster of experiments, the one with the smallest error bar is the one from SLD from 1995. So this is the result that's at the very top of this plot. Let's now compare that result with the results that came afterwards. So we're going to be looking at this cluster of results that happened between 1996 and 2004, and these results had error bars that ranged from 1.7 to 4.9 femtoseconds. And we're going to be comparing that with the SLD result that we just saw. Okay, so now we've plotted those results here. Again, the bottom result is SLD, which was the top Gaussian that we saw in the previous plot. Again, we've changed the scale, so again, the blue line width is the Belle error bar. Now, this set of results from 1996 to 2004 starts to have error bars that are small enough that the Belle error bar, which is represented by the width of the blue line, starts to become a little bit relevant in our comparisons. But nonetheless, we can again see that the results are again generally sensible in comparison with the later, more precise Belle result. So here we show a comparison of all of the other results with the Belle result from 2014. And we can see that the error bars go from huge in 1982 to very, very small in, say, 2000 or 2004. We can also see that the deviations of the measured results from some value that's very close to 290 femtoseconds are also reducing with time. So if we have Gaussian uncertainties that are correctly evaluated and are getting smaller with time, then we should expect that the measured results should converge to the true value as time goes along. Okay, so now let's discuss our results a little bit. So at the beginning of the video, we asked the following. We asked if one experiment measures the Tau lifetime to be 290 plus or minus 10 femtoseconds. Does that mean that the true value of the Tau lifetime is between 280 and 300 femtoseconds? And no, it doesn't mean that. But what does it mean? So, assuming that the experiment is quoting a Gaussian error, a result of 290 plus or minus 10 femtoseconds means the following. It means that if the experiment were repeated many, many times, the measured results would be Gaussian distributed around the unknown true value, and the standard deviation sigma of that Gaussian would be 10 femtoseconds. At the same time, the actual experiment was only conducted once, and the result that they got that one time they conducted the experiment was 290 femtoseconds. Now, sometimes people believe that Gaussian errors imply that the true value is Gaussian distributed around the measured value. And I hope that this plot makes clear that that's not the case. Instead, what's happening is that the measured results are Gaussian distributed around the true value. And as we can see here, we have many measured results, and they're Gaussian distributed around the same true value. Now, technically, this hypothetical result of 290 plus or minus 10 femtoseconds alone doesn't tell you what the true value is or the probability that it's in a particular range. In order to get that, you need to combine the result with Bayes' theorem. We're not going to go into that here, but details can be found in the videos in the Bayesian playlist. Okay, so let's summarize. So here we've seen 1. How the measured value of the lifetime of the Tau Lepton changed over a 30-year period. 2. How the experimental precision improved in that time. 3. That the results over the 30 years are, in retrospect, in good agreement with the most recent, most precise result that we have from the Belle experiment. 4. We've seen that the experimental uncertainties appear to have been estimated well by the various experiments over those 30 years. And lastly, we've also seen how to interpret a Gaussian error bar.